Hello, my name is Han Tran, and in this video we're going to be taking a look at some reactor dynamics. And so we're going to be looking at this problem that outlines a reactor, its coolant, and the reaction that occurs in the tank. And so we are given these parameters, and in this video we're going to use those parameters and our knowledge about material balances to develop ordinary differential equations that we can use to help us simulate the effects on the concentration and the temperature inside the tank. So let's take a look at the problem. So here we have our problem, and it tells us that we have a CSTR. So a CSTR is a continuously stirred tank reactor. So we know we have a tank, and it is being continuously stirred. Now, the fact that it's continuously stirred is important because what that tells us is that the concentration and the temperature that's inside the tank is what is coming outside of the tank. Now, we are also told that we have a coolant temperature, so that basically means that we have a cooling jacket around, or at least it tells us that we have a cooling jacket around our reactor that allows us to essentially act as a regulator for the reactor, so it regulates the temperature. And so there's a certain temperature inside this coolant jacket that it refers to here as TC. That is the coolant temperature. And we are also told that we have an exothermic irreversible first order reaction A to B. So there's a reaction going on that is from A to B. And so we want to write the ordinary differential equations that deal with the concentration of A and the reactor temperature. So what we want to talk about or go about writing an equation for is the change in the concentration over time, and that's going to tell us what the concentration is in the tank at a certain time. We also want to talk about the change in temperature over time, and this is going to give us a temperature of the reactor at any given time. And so that's kind of the information that we are given above, and then we are given a bunch of conditions, parameters, and values for these parameters in the table below. So let's take a look at those and take a look at the information that we can gather from it. We have a parameter called Q, and we are told that it is 100 liters per minute. So we want to figure out what this parameter Q is. Well, if it's per minute, we can kind of know that it is some form of rate. And we are told that it's liters per minute, so we're going to assume that it is the flow rate, right? The rate at which liquid is being added into the reactor and out of the reactor. And we are only given one rate, and so we're just going to say that the flow rates going in and the flow rates going out of the tank are the same. So this is flow rate, and we are assuming that Q in equals Q out, flow rate in equals flow rate out equals the flow rate. Now we are given a parameter called CAI. So initially looking at it, the assumption could be made that it's the concentration of A. Now the I could either mean initial or going in, but we are also given this parameter on the right over here that is CA of 0. And we can see that the CA of 0 is less than the CAI, and so it can be assumed that the initial concentration is going to be less than any other concentration. And so we are going to say that this Ca0, that is 0.5 moles per liter, is the initial concentration. And the CAI, that is 1 mole per liter, is the concentration into the reactor, or the tank. Now we are given a tau I, and it is in Kelvin, so this means that we can assume that this tau I, that is 350 Kelvin, is a temperature. Now, is it the initial temperature or the temperature of what is going into the tank? We also have on the right over here more Kelvin units that are also temperatures, so we have T C of 0 and T0. Similar to the concentration of 0 here, we can assume that is the initial temperature. So the tau I, that is 350 Kelvin, would then mean that it is the temperature into the tank, which would make this Tc of 0, that is 300 Kelvin, some initial temperature, but we are also told up here that we have a coolant temperature that is Tc, so we can make the assumption that this is the initial coolant temperature, making this T0, that is 350 Kelvin, the initial tank temperature. Now we are also given volume, so we are only given one volume, which means that the volume in this case is constant. So we have V parameter is 100 liters, and that is the volume in the tank. And then we have a parameter rho, and this is grams per liter. And so we are going to assume that this is the density. So it is 1,000 grams per liter. That is the density. And then we are also given the parameter capital C, and that is 0.239 joules per gram Kelvin. And so what that joules is telling us, and the unit, that is joules per gram Kelvin, we can assume that it is heat capacity of what is in the tank. And we are only given one, so we can assume that that's the heat capacity for what is in the tank, and it doesn't change, it's constant. We are also given a negative delta HR parameter, and delta H is often representative of enthalpy, and so we have 5 times 10 to the 4th joules per mole. And we are told up here that it is an exothermic reaction, and we know that enthalpy, if it's exothermic, would be negative. So according to, if we were to remember the way that reactions occur, it is reactants minus products. And so that would give us a negative number for exothermic reactions. But since it is the negative delta AHR, so we'll have a negative of a negative, that's going to give us a positive value, which is what we have here for the 5 times 10 to the 4th. So that checks out. So that is our enthalpy parameter. So if we take a look over here on the right, we have a parameter E/R and a parameter K naught. So we have E over R parameter and a parameter K naught. So the E over R parameter is 8,750 Kelvin, and the K naught parameter is 7.2 times 10 to the 10th minutes to the negative 1. And so this E over R is actually the activation energy over gas constant R, and then this K naught is a constant that is used in the Arrhenius equation. So these two parameters actually help us write the Arrhenius equation, which is a formula for a reaction rate dependent on temperature. So this equation is K reaction rate equals constant multiplied by E to the negative activation energy over gas constant R times temperature. So here we have K naught as the constant and E to the negative activation energy over R divided by gas constant R times temperature. So the gas constants cancel out, and that leaves us with K naught E, so exponent of negative 8,750 over temperature. So we can leave it as E, and so that would give us 7.2 times 10 to the 10th. So we'll replace both the K naught and the activation energy over gas constant R. So that gives us 7.2 times 10 to the 10th times E to the negative 8,750 over temperature. Again, this reaction rate is dependent on temperature. And since now we have the reaction rate, we know that the reaction rate is the Arrhenius reaction rate multiplied by the concentration, and what that gives us is the rate of accumulation. And so we can rewrite it as rate of accumulation equals the reaction rate multiplied by the concentration of A. And then the last parameter we have here is UA, that is 5 times 10 to the 4th joule per minute Kelvin. So what this is it is the heat transfer constant. And so what this heat transfer constant is, it's the constant for the transfer of heat between the tank and the cooling jacket. And so that's actually going to be this constant, and when we are dealing with a transfer of heat, it is because there is a difference in temperature. between two objects, and so it is dependent on that difference. And so we're going to do the heat transfer constant multiplied by the difference. So we'll have the temperature of the tank minus the temperature of the coolant. And those are all of our given parameters and information all laid out into the terms as well as the parameters and the values. And so now we can begin writing our differential equations. So when looking at writing differential equations that deals with a reaction and a change in concentration or a change in temperature, a general formula that we can follow is the flow in minus the flow out minus the accumulation. So for the concentration, we want the change in concentration of A over time, but as we can see here, the units for the concentration is mole per liter. So the concentration of A is volume dependent. Depending on how much volume there will be a greater concentration. If there's more of a liquid, there's going to be more of the stuff that's in the liquid. And so we want to make sure that we include volume in this, but volume is constant, so we can keep it out of the differential equation. And so this is going to first start with the flow in. So we have the rate, flow rate, that is Q, but as we established here, the flow rate in equals the flow rate out equals the flow rate. So we can have the flow rate be the same for both in and out of the tank. And so we just want to have it be the concentration going in. So the concentration going in here. So we have concentration in, which we are given as a parameter, multiplied by, since it is a continuously stirred tank, we know that whatever concentration is inside the tank is also the concentration that is leaving the tank. And so we can just have that as the concentration A. And so that has our flow in checked, flow out checked, and now we have our accumulation. Well, if we go down here, when we were talking about our Arrhenius equation, we developed the rate of accumulation, that is the so we have minus, and so we have the rate of accumulation based on this Arrhenius equation is this parameter K, which is the reaction rate, multiplied by the amount of the concentration of A. And so we will copy that up here. Reaction rate multiplied by the concentration of A. Depending on how much of this material there is, determines the reaction rate. On top of that, the concentration is based on volume, and so we have to make sure that we include volume. So now what we can do is we can, since volume is constant, we can divide both sides by volume, and that will leave us with just the differential equation of the change in concentration over the change in time is equal to the flow rate over the volume multiplied by the concentration going into the tank minus by the concentration of the tank minus by the reaction rate multiplied by the concentration in the tank. And that is our differential equation for the concentration. So now that we have written the change in concentration over change in time equation, let's take a look at the differential equation for temperature. And so in order to write a differential equation that will show us the change in temperature over a change in time, we can take a look at the internal energy of the tank, because the internal energy of the tank is calculated by the heat capacity multiplied by the amount that there is multiplied by the temperature. Well, we are given the heat capacity, and the temperature is changing, so we have a change in temperature over a change in time. And then we are given the amount that is in the tank, that is the volume. But if we look at the parameters that we are given and the units of the values, volume is liters, and our heat capacity, though, is in mass with grams. And so we have to convert liters into its mass in grams. And we can do that using the density that we are given. So if we multiply density by volume, that's going to give us the amount that we have. And then we have the heat capacity here. And then we have the temperature here. And so that's going to be the internal energy, and it's going to be a change in internal energy based on the change in temperature, but that change in internal energy is going to be due to the total enthalpy. So we have enthalpy that is going into the tank because there's a flow going into the tank, but then we also have enthalpy going out of the tank because there's flow coming out of the tank. And so that is our total enthalpy. But we also have another heat transfer between the tank and the coolant in the cooling jacket. And so if we take a look down here at our parameters that we already established, we talked about the heat transfer constant and how the heat transfer constant multiplied by the difference between the temperature in the tank and the coolant temperature actually gives us the heat transfer between the tank and the cooling jacket. So that's going to be minus, because the temperature is being transferred from the tank away out of the tank to the cooling jacket. And so we have the heat transfer constant multiplied by the temperature in the tank minus the coolant temperature. And so again, here we have the density multiplied by the volume multiplied by the heat capacity multiplied by the change in temperature over a change in time. And so what is the total enthalpy? How do we know what the enthalpy in is and what the enthalpy out is? Well, we know that there is a flow. The flow is going in and out of the tank, and the flow rate is constant. So we have the flow rate being constant. And then we also have the heat capacity. That tells us what the energy flowing in and out of the tank is. So if we multiply the heat capacity by the flow rate, that gives us the energy going in and out of the tank, but we also have to multiply that by the temperature. So since the flow rate and the heat capacity is constant for both in and out of the tank, we can take that out and keep it constant, but the temperature into the tank and out of the tank is not constant. So we have to have it as a difference of in and out, and so we have the flow of the temperature of the flow going in, so that's going to be temperature in, minus the temperature of the flow going out, that's going to be just the temperature inside the tank. Since the tank is continuously stirred, whatever is inside the tank is also what is leaving the tank. Now, same thing as we did before, if we take a look at the flow rate over here, it is in the volume liters, and so again we need to use the density to convert this liter into grams to match the heat capacity. And then, again, we have the heat transfer, so that's going to be the heat transfer constant multiplied by the difference between the temperature in the tank and the coolant temperature. But we're missing one more thing, and that is the temperature change due to the reaction. So we know that this is an exothermic reaction, so there's going to be heat energy added to the tank due to the reaction. So we're going to add, and the energy added to the reaction is going to be based on the rate of the reaction, and that's going to be multiplied by the concentration of the amount that's in the tank, because depending on how much there is in the tank, depending on the concentration, the reaction may be quicker or slower. And the concentration is based on the volume, the amount that's in the tank. And so this is the reaction rate, but we also have the energy change due to the reaction rate, and that's given as a parameter. This is given, we are given the enthalpy, that is 5 times 10 to the 4th joules per mole. So that is all multiplied by the enthalpy. And so the enthalpy of the reaction, and so that actually accounts for the temperature change. So now what we want to do is we want to isolate the change in temperature over change in time on the left there. And so we're going to divide both sides by the density, the volume, and the heat capacity. So that's going to leave us with the change in temperature over change in time is equal to the flow rate divided by the volume multiplied by the difference of the temperature going in minus the temperature in the tank plus the enthalpy of the reaction multiplied by the rate of the reaction multiplied by the concentration of A in the tank divided by the density multiplied by the heat capacity minus the heat transfer constant multiplied by the difference of the temperature in the tank minus the temperature of the coolant divided by the density multiplied by the volume multiplied by the heat capacity. That gives us our final differential equations for the change in concentration over a change in time and for our change in temperature over a change in time.